So I just want to make a few other comments about relative trisections and then switch gears completely and tell you about applying final factor for a trisection. So comments about the relative trisections. You can, so here's our picture. In this case, remember, yellow represents, it's not a fold, but simply the image of part of the boundary of the four manifold. Four manifold maps the disk, and up inside the disk, sitting over this, over the yellow circle is a surface bundle over the circle, and then sitting over the interior, the boundary part, what sits over the interior is a bunch of solid tori connecting to this disk, so that one of these surfaces, and then follow the next line, there you get a page. The image of this point is a surface with boundary, whose boundary on the boundary of four manifold is the binding of the multi-composition. So that's a knot or link in the three manifold. And then we have this sort of standard picture for what may happen. And I'll just go in measure. I'm not putting the dots here, but so the genus here, this is a surface of genus G, then this will be a surface of some other lower genus, and let's say P, it'll be a surface of genus whatever, G minus the N, if the N is the number of folds there. By the way, if you read material about relative trisections, there's just lots of integers to keep track of, and I'm responsible for some of the conventions, and I wasn't really thinking very carefully, and I can't remember how I did it. My co-authors had ideas, and I don't care. Just there's numbers to keep track of, obviously, which are just number of boundary components, genus, how many things have cusp, how many things don't have cusp, what the genus of the page is, all that. And you can work it out. But the crucial point is you again you get so a relative trisection from a relative trisection. Associated with that, there's a relative trisection diagram. And what is that relative trisection diagram? We just look at what sits over the red, blue, and green curves, and red, blue, and green arcs, those are compression bodies. You look at, well, one way to say it is take metrics on everything, so that then you have gradient flow lines, gradient flows, and then you have these are in this is surface, then going that way. These are index 2 critical points, a collection of index 2 critical points, which flow, they're downward descending manifolds, are disks that hit the surface of a collection of circles, and that'll give you some sigma, alpha, and gamma. But the important point is that the number of curves in alpha, well, you should expect the number of curves in alpha to be the same as the number of curves in beta, the same as the number of curves in gamma, but that's less than or equal to the genus of sigma. It's not necessarily equal to the genus of sigma, that's all. And what is surprising, and I certainly didn't realize until I'm thinking about this carefully with Nick Castro and so on, is that these, so alpha, gamma, beta, gamma are collections of simple closed curves. And this actually completely determines the four manifold X and its trisection up to 51. And you might say, why is that not obvious? That was true in dimension, in the closed case. And the reason it's not immediately obvious in the case with boundary is what this So this fact is due to Castro, myself, and Juanita, too. And at least as far as we can tell, it took some work to prove it. And the difference there is that so why is this? Why not obvious? Well, here's what sigma alpha theta gamma obviously gives you. You take sigma across the disk, and then the alpha curves give you a compression body, which I'll call, so C sub alpha equals sigma across an interval, union 2 nanovolts attached to an alpha. And the same thing for C beta and so on. So I'm done there's enough room now. And so from this, you can get a surface across this, and then you can attach the alpha compression body and thicken it. And you can attach the beta compression body and thicken it. And you can attach the gamma compression body and thicken it. And now you get that much is fine. And this is what is standardly done in the Hager floor world. This is how what the obvious data you get from some sort of incomplete triple of curve systems like this. But the problem is then you have all kinds of boundary, and what you need to do is how do you fill this in? And the point was that in there's more stuff to put here, and the point is that in the closed case, these are handle bodies that just end. There's no boundary here. And so then you just get this nice connection of S1 cross S2s, connection of S1 cross S2s, connection of S1 cross S2s. But here and then you can just appeal to Poincaré and just fill them in immediately, which is not trivial, but old material. Here, this is not, just this part here is actually a 3 manifold boundary by itself. So I don't have time to go into the details. That's what we worked out in our paper. But roughly speaking, what you do is if you have a tin can picture in your head, you put the tin can back together first, and then fill it in. So you figure out that there's a unique way to put on surface cross I here, surface cross I here, surface cross I here, put the caps on, and then you connect some of the S1 cross S2 boundary components that you can fill in uniquely. That's all I'm going to say about that. And there's a nice algorithm to do it by drawing some arcs and so on. The other cool fact, why all this is all useful, so relative trisections are useful. And again, Rob and I didn't know this. The motivation for what Rob and I had, we thought of all of this coming from inspired by work with Lefschetz vibrations. And Lefschetz vibrations were standardly thought of as maps to a surface from a closed manifold, or if it was a manifold boundary, you would map to a disk, and you get an open boson map. So we were just sort of blindly saying, well, what do we have that might mimic that? And this just fell into place. We just sort of, okay, there it is. Remote compatibility. We didn't think much more about it, but Nick Castro showed that thesis that you can actually glue them together. The open boson match. So remember, they induce the open boson with boundary, and so if you have two relatively trisected formats with boundary, and then you have a diffeomorphism, orientation reversing diffeomorphism with boundary one to the other, respecting the open books, then you can glue everything together and you actually get a trisection on the whole thing. And one reason that's not so obvious is I think it's really important to have the Morse theory, Morse two function perspective in mind. That doesn't help at all with seeing the gluing result. It's kind of like you glue these pictures, you got this tin can mapping down here, you got another tin can mapping down here, and how are you going to glue them together? You can stack them on top of each other, you still have boundary. You got to glue them together along the entire boundary, and it really feels like everything's got to wrap around, and there's just a mess, and it doesn't work. So there is some way to probably prove that, where you sort of fold stuff around and then get some non-trisected Morse 2 function, and then you clean it up or something. But there's a this proof is very simple, actually, just by thinking about the definitions of pieces and seeing if you get antibodies. It's worth reading. It's straightforward when it's sort of thing is straightforward when you understand it, but not when you understand it. Anyway, that's all. And then what Nick and Anita and I did after that was figure out diagrammatically how to put it together. I'm not at that. So I think that's all I want to say, unless there are questions about relative trisections.
Does Castro need to appeal to any fancy contact geometry?
No. I mean, where you might appeal to fancy contact geometries if you were trying to, so what you might do, for example, you might say, I want to, suppose you only knew, if you want to prove that trisections exist on closed manifolds, and you only knew how to construct them on manifolds of boundary, then you've got manifold 2 pieces constructed on either half. Now you need to know that I can get the open books to match. And one way to do that would be to, say that I can get the underlying contact structure of the boundary to be the same, and then you should remove something like that. But that's not really how it works. Now, he's already assuming that typical fancy contact geometry stuff is used to get open books to match. If they already do, you're fine. The general problem with classifying, so say you've done this twice, you want to look together, and then you don't know if the open books match. The general problem with classifying open books on a given 3 manifold is hard, and lots to be said about this. But in all the cases where it's been used so far, we just know what the open book is. This page is annulus, and monodrome is something simple. Okay, anything else? So group trisections. So the idea is if you take I1 of the trisection, what do you get? Well, you want to think I've got my trisection. I've got x1 intersect x2 intersect x3. Let's just think about first just all the different pieces you get. That is included into x1 intersect x2 and x2 intersect x3 and x3 intersect x1. And those are included in x1 and x2 and x3. Let's see let's I want to do x3. Why does it something like that? I want to go the other way. That's the trick, I think. I didn't want the map to look like that. What I wanted the map to look like, what I wanted what that arrow to look like. Let's label it afterwards and figure out. I want it to look more like a cube. You'll see. So I want it to be. Okay, so what does this make this? That has to be x1, and that has to be x2, and that has to be x3. That's right. It's the one that's not included there. Yeah. And then all of those are included in x. So of course, you put your base point here, then you get induced maps on I1 all the way through, and this is a surface. Surface. These are differomorphic to connect stones. Okay, I'm gonna do work with balanced trisections all the way through. Just, you can do it in the unbalanced case, but it's just easier. I don't have to write KI so many times. Sorry, G. Yeah, these are hand bodies, S1 cross S1 cross B2s. Those are our hand bodies. And these are connect sums of K. And so they're all right back here. And so when you apply pi 1 to everything, you get a, let me see how to say this. Be slightly, so if I apply pi to everything, then I get a group here that is isomorphic to the standard surface group. And I get a group here that's isomorphic to the standard free group. I get a group here that's isomorphic to standard G generators. I want to think, if I fix all these isomorphisms, this is kind of a subtlety. So think of that as part of the data. And if you think of that as part of the data, then you actually get on the nose the standard surface group of genus G, where the surface group of genus G means, so the surface group of genus G and the group of generated A1, B1, B2, and in relation to the product combinators. And free group, they have free group of rank K and free group of rank G and free group of rank K. And I was right here. Anyway. So putting this all together, this we get a diagram. Map from surface group of rank G onto free group of rank G, free group of rank G, free group of rank G, and then those map to free group of rank K. And that maps to something G, is pi 1. These are all surjections. And they're all surjections, and all the squares in their communities. Perhaps better to see it as a three-dimensional thing. So this is a thing called a push-out cube. What that means is each of the, on every square, every face here, you have push out, which means that each of these is the universal object with respect to these two incoming maps. Or in other words, this is this free product that mod the image of those. Okay. So it's exactly what Dan Camden here says. Are there any questions about what this is? This is just applying that by one function to everything. And applying standard and fixing some standard isomorphisms. Okay, so we call this, so a diagram like this of surjective maps, a cube of surjective maps of this kind, where you have free groups of some rank G, these are free groups of some rank K. We start with a surface group of rank G, a diagram of surface groups of maps. We call that basically a trisection of the group. some sort of way. It's a kind of presentation of the group. And so this is work with Aaron Abrams, by the way. And and so the claim, so then you can ask the question, by the way, this could be the trivial group. It could have interesting trisections, right? Or manifolds. So the first claim is that the group trisection acts as German X. Any group trisection uniquely comes from and uniquely determines a trisection. Uniquely means up to diffeomorphism, a trisected. Oh, this is the closed case. I should have said that. I've gone back to the closed case. I think it's very interesting to think about the relative case in the setting, but we haven't done that. So that's why if it wasn't closed, then you'd have a surface boundary, you'd have more generators, and you wouldn't have this relations that would be free. And so this is, maybe I just want to try to sketch why this is true. But if you believe that, so when we wrote our paper, we sort of said it's like, there's the set of all group trisections, and there's a set of four manifolds with trisected four manifolds. This is mapped from one to the other. And there's also a notion of stabilization of trisected of group trisections, which comes directly from so stabilize them. And that comes to, if you figure out, once you believe that, then you can take a group trisection, turn it into a trisected four manifold, stabilize that four manifold, turn it back into a group trisection, and figure out what you did purely theoretically. And you just ended up increasing, just adding some adding 6 generators here if you're doing the balance stabilization, adding 3 here and 1 here, and you can figure out where the generators go. It's not that hard. So a cool fact, for example, is that just change the paper there, make sure I can state it correctly. Cool fact is that the smooth 4-dimensional Meier conjecture is equivalent to the following statement. Every 3K trisection of trivial group is stably equivalent to the trivial trisection. Where the trivial trisection is just, so genus 0 means the trivial group, and rank 0 means trivial group. So you put trivial groups everywhere and you have a group trisection. Roughly speaking, the idea here, I'm not going to write down detail. I'll try to write down some details for this. But the idea here is that if it's 3K complicated, that means the genus is 3K. That's called a GK trisection. So if you have 3K and K, you can figure out that the 4 manifold, this implies that the 4 manifold has the same Euler characteristic as the 4 sigma, which is 2. So you can figure out that. And then a nice, actually a good exercise that like wraps up many things in algebraic topology is to show that a closed-oriented four-manifold, a closed-oriented, simply connected four-manifold or the charge 2 is homotopy equivalent to S4. I guess I didn't have to say oriented if it's pi 1 equals 0, but equivalent to S4. I don't think I can do that on the fly. Just pi 1 equals 0 and other characteristic equals 2 allows you to figure out all the higher homology groups that are all trivial until you get to, it's not. But so this means that if you have a 3kk trisection, the Euler characteristic would be 2, it's a trivial group, so it's pi 1 zeros equals 1. Same thing here. So therefore, whatever four manifold you're producing from such a thing is homotopy equivalent to S4, and you want to prove it's diffeomorphic to S4. If you prove the group trisection is stably equivalent to the trivial one, then you're simultaneously proving that the trisection of the four manifold is stably equivalent to the trivial trisection of, which has to be a trisection of S4. The genus is only, if you have a four manifold with a 0,0 trisection, then it is S4. So what is amazing about this is that it turns out that smooth four-dimensional Poincare conjecture is a statement about group theory. Because nothing in the quotes here involves smooth anything.
Do the stabilization moves are they like Andrews-Curtis moves? So
Well, they're literally just adding, they're adding some new generators here. New generators everywhere in a very, prescribed way. And then we say exactly where these generators go. They're not, they're not handle slides. They're just like the stabilization part. The handle slides,
so that seems like a better group theory statement than
I suppose, yeah.
Andrews-Curtis.
Yeah. That's right. But the Andrews-Curtis it's not equivalent. So Andrews-Curtis, balanced presentation of the trivial group, that means presentation of the trivial group, the same number of generators and relations, they can be used to produce homotopy force spheres. And if the Andrews-Curtis conjecture is true, which is that they can be reduced to the trivial thing by these moves, then all those homotopy force spheres would be smoothly diffeomorphic S4. But it doesn't mean it is not known if all homotopy force spheres are Andrews-Curtis force spheres. So that it's a much weaker thing. And the other thing cool, so let me sketch it. I think one of the nicest things about this is this fact here needs the three-dimensional Poincare conjecture. And it's really because you need to be able to recognize a three-manifold from its fundamental group. And prototype example is recognizing S3 from its fundamental group. So it's like a strong consequence to me of the three-dimensional Poincare conjecture, which is also a statement about group theory also, because if you do the same reason, then could have started this way, do the same thing for Hagar splitting. For Hagar splitting, you just have surface group, two free groups, and this three-manifold group, right? And that determines the three-manifold in a way I'll explain. And then so the three-dimensional Poincare conjecture can be equivalently stated. And this is this paper by John Stallings called "How Not to Prove the Poincare Conjecture," which really inspired this whole. I wanted to title this paper "How Not to Prove this Smooth Four-Dimensional Poincare Conjecture" in honor of John Stallings, but so anyway, there's So the other miracle is that so the smooth three-dimensional Markov conjecture was proved with, really hard analysis and flows, Riemannian geometry and flows and so forth. So you could say that all that analysis is required to prove this really slippery fact in group theory, which is kind of impossible. Okay, so let me try and prove that a group trisection uniquely determines okay. So we're given this trisection of a group G. So we're going to start to build the format, right? So let me remind you, I started in SB surjections. Let's do this. Let's start with this much, right? So we build 4, 5. Well, so part of the fact that it's a trisection is that I'll circle stuff as I use it. So using from the fact that I'm starting with a surface group, okay, that's easy. A surface group determines a surface. So I just take surface, G is G, cross this. What I need is some handlebodies. So given this, the lemma is that for any surjective map, F of a surface group to a free group of rank G, sorry, SG, free group of rank G, there's a unique, I'm going to write this way now, I'm writing it as pi1 of a surface. So in this case, the point is, this is the fixing and identification of it. This is not just some random group, possibly it's an actual pi1 of a particular surface. And that's what we're really using by doing generation, particular generators there. There exists unique handlebody H with the surface equal to the boundary of HG such that the inclusion map from surface H induces star that so any surjection onto a free group of rank. We know that if you have a handlebody whose boundary is a given surface, then the inclusion, that the pi1 of the handlebody is a free group of rank G, and the inclusion is surjective because you get a regenerator. But what's not clear is that you can always, that there actually is, first of all, it's not clear there actually is such a handlebody, and secondly, it's not clear that it's unique. So that there is such a handlebody. The story here is that Rob Kirby and I were stuck on that thing. And finally, Rob figured out what was true, and then we called our neighbors to verify if he really agreed with us that it was true, and he said yes. And you, being Rob Kirby, asked me that on my qualifying exam. So this is some sort of standard. This is a standard fact in three-dimensional topology, but Rob didn't remember it. I didn't remember it. Or something. But the argument is kind of cool. So you look at this. So what you do is you construct a map, a continuous map first. Let's call it H or something, from a surface of G is G to a wedge of GDS ones, realizing so that H star So you just, all you're doing is you basically say, I've got generators here. You look at every element, every generator here and say, where does it go, wrap around. That gives you a way to map all the one cells of your surface onto onto this thing for each of these generators. And then because you've satisfied the relation here, because it's mapped on pi1, well, the surface will extend continuously to this thing. And then you perturb, maybe I'll say what's like, here's how we were trying to do it. We're saying, okay, let's take the kernel of this map. The kernel of this map should be, if we can just represent the kernel of that map by collection of simple closed curves, like this, then we're good. Because the kernel, the simple closed curves on the boundary of the surface are precisely the things that die when you fill in antibodies. So all we have to do is find a collection of G simple closed curves here that represent this kernel, that's generating the kernel. The problem is an arbitrary element of pi1 of the surface may not be representable by a simple closed curve on the surface. And that's sort of what a lot of the Stallings paper is about, is how hard it is to represent. To have a criterion for deciding whether an element of pi1 of the surface can be represented by a simple closed curve. So that's what we're stuck on. So what you do instead is you perturb this to be H to be transverse to some, a point in each S1. Take that now is S1. It's got a surface mapping down here. Take a point in the interior of each S1 and make this map transverse. Now you take the inverse images of those points. And the inverse image of the points are circles. Now they are, because it's transverse, they're actually smooth submanifolds. They're collections of circles. Of circles in the surface. But there may be thousands of them. Like this map may wander back and forth across. So there may be like boom, 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 and then boom, this, lots. And then you should also be nervous about saying transverse when you're not mapping to a manifold. But that you just say, well, that's okay. Because the transverseness is happening in the manifold part. So there's something you said there. So you get these collections of circles here, and then then build the antibody H, G by attaching handles to these circles. To these circles. And well, what if you had thousands of them? That's okay because they're disjoint circles because these are disjoint points, so they're disjoint collection of circles. So you take surface cross I, attach two handles to it, and you're going to get, after you do that, the other end would be some surface. And the claim is that surface is a collection of spheres. And the reason it's a collection of spheres rather than hydrogenous things is because if there was any homogeneous left over, this couldn't be a surjective map. That's the upshot. And so it's a collection of spheres, so they fill in spheres. So that's a neat three-manifold topology argument. The other part, the uniqueness, is important also, because that'll give me a handle body to attach. But I need to know that handle body is unique, and I need to know it's unique up to what? Unique up to, they're fillings of the surface. So they're unique rel boundaries. So I've got, so for the uniqueness part, here, so uniqueness. So we call it the H and H prime are two solutions to this problem. So in other words, I sort of schematically I have this surface and it bounds H and it also bounds H prime. So H and H prime have a common boundary. What I really want to do is show that every circle every simple closed curve that bounds an embedded disk in H bounds an embedded disk in H prime. And if I can do that, then I can show that then I can basically take all the curves that I can construct an isomorphism, a diffeomorphism H to H prime by first building it on those disks, and then the remainder would be a ball. Want to show every simple closed curve sigma bounding disk in H1 and H also bounds in H prime. Well, for this, I always forget what the theorems are. These are some theorems in three-dimensional topology. Okay. Right. So I'll write this down. Take a curve here that bounds an embedded disk here. It's an embedded curve here, it bounds an embedded disk here. Therefore, it's in the kernel of the map. It's in the kernel of F. So it bounds a mapped in disk here. And you want to know that just a topologically mapped in disk because it dies in pi 1 here. And then Dane's lemma says that in that situation, Dane's lemma is a lemma in three-dimensional topology that says that if you have a single closed curve on the boundary of the three-manifold that is trivial in pi 1 of the three-manifold, then it bounds an embedded disk. So it's a way to produce disks. And this is as a hard theorem. False proof by Dane and true proof by complicated calculus. That's okay, so then doing that, you can produce, so you get these unique antibodies, H alpha, H beta, H gamma. And now the next thing you know is that you have some four-manifold with three boundary components. And these three boundary components are all three manifolds. And you want to know what their fundamental group is. And well, the fundamental group of each of those three manifolds can be computed by Van Kampen's theorem, because it's pi 1 of this antibody included to pi 1 of this antibody, along with this surface group. So it's precisely these three groups of rank K. So by Van Kampen's theorem, three manifolds with pi 1 equal to free group of rank K. And we want to say that this implies that they're actually different homomorphic, there's three dimensions the same as diffeomorphic, to connect to some of S1 cross B groups. S1 cross S2, sorry. So the first case is if K equals 0, we're saying if pi 1 is trivial, you want to know it's homomorphic S3, and that's the smooth quantum ring conjecture. The higher, the case where K is, K equals 0, this is the three-dimensional quantum ring conjecture. Let's see. What do you say? Right. So what it became bigger than 0. What you do again is a result of Stallings, who proved something called Canadian's conjecture, which says that if you have a three-manifold whose fundamental group splits as a free product, then that splitting as a free product actually corresponds to a connect sum decomposition of the three-manifold. So pi 1 free product equals connect sum decomposition. So that means that this thing can, using Stallings, this three manifolds can connect to some of things with fundamental group Z. And then right, so then you can show that if you have a fundamental group Z, you have to use, you need the Witten sphere theorem. So you use pretty much everything. There's hard theorems, Witten sphere theorems. And I'm just citing them, give you inside, give you S2 support long. I mean, once you get that, you've got a 3-manifold who's fundamental, you've got to connect some of 3 manifolds who's fundamental to Z. Now you take each one of those, you need to find a 2-sphere to cut along, and so the remaining part is a ball. And you need to show the remaining part, you need to find those spheres. And so that's what these things called Witten sphere theorems together work to give you these spheres that you can cut further along each of the pi1 equals Z summand. You can cut along a sphere and you get something that's homotopic to a 3-ball, and therefore by the 3-dimensional quantum gradient conjecture, diffeomorphic to a 3-ball. And so that plus Perelman gives. So that's just a whirlwind tour, but it's just neat because it uses all those facts. Okay. And then finally, that tells you that those things are connected some special cross S2s, so you can fill them in. Fill them in. So finally, use, as usual, use Laplace and Meier. I don't want to say anything about this. Yeah, I guess the uniqueness part is not so hard, so I can just talk about it. I mean, I went on to, so that means there is that's not that uniqueness was just the uniqueness of the handle bodies. Now I'd like to say that this data, so I know that this data produces a 4-manifold trisected with this data, but if I had a different, what I need to know now is what I really want to know is if I started with a trisected 4-manifold, extracted its group trisection, forgot about the 4-manifold, built this 4-manifold, and then compared the 2 4-manifolds, they would be diffeomorphic. But that's sort of almost obvious. I mean, the diffeomorphism will happen. We know the surface will be the same, and then the hand bodies will be, in a sense, that was all the unique. I guess that really does boil down to that uniqueness as well. So, and yeah, that's it. Maybe I'll stop in 1 second after saying that there's a fundamental difference between this. So this can be just thought of as a way of describing a 4-manifold. So you want to actually pick your favorite group and want to write down a trisection. What's hard about it? It's not hard to find. These surjections mean you need to find, you need to generate it with group these have, you need to generate with K generators in 3 different ways. Okay, you can do that. Work backwards, that means that these 2 ways of generating sort of really come from a way of generating G generators and some relations. Okay, so that's not that hard. What's hard is getting all the way back to here and needing this to be a surface group, which means it needs to have, you're not generating, if this is a free group, it's easy, but you've got that extra relation that has to somehow magically be satisfied at the last minute if you work backwards. So it's kind of the dual capping off problem. So I think there's always a capping off problem for 4-manifolds, but it's at this end. The few times I've tried to do this from scratch. The other thing interesting about this is how does this describe a 4-manifold? It describes the images of, how do you write this down? You write down the generators and where they go. When you write down a trisection diagram, you're not doing that. You're describing the kernels of these maps. So there's something different about describing a map and describing its kernel. And that's also some sort of dual thing that I haven't really absorbed. Anyway, there it is for the group theorists to figure out. And Jeff should be back. A few more examples.
It is a corollary that any finitely presented group is a function of the surface. I don't know.
Oh, that's right. Yeah. And even, yeah, it's probably obvious, but that it has a trisection is not so obvious. Because any finite representative group is one of the four manifold, and that can be done in totally different ways, and then, yeah, that's interesting. The other thing is like, so a trisection of a group has a four manifold, therefore it has H1, H2, and Pi2, and Pi3, and intersection form and everything, right, in there. So there's a trisection of a group, I mean, the trisections of the trivial group are all simply connected four manifolds, which are crazy, so somehow